So in this video, we're going to continue with acids, and we're going to look at the core practical, which is preparing a salt from an insoluble base. So in the last video, we saw that if you react an acid with a base, you form salt and water. So if you're trying to prepare a salt, then you're going to react an acid and a base. You could also react an acid and a metal to make a salt, but in this practical, we're going to be reacting an acid and a base. And in this one, we are going to be using an insoluble base. So it's a base that doesn't dissolve, so it is a solid. Okay, so your base is going to be a solid. Your acid is always going to be in liquid form, always, always, always. So what you're going to be doing is you're going to be taking a base, which is a solid, and you're going to be adding it to an acid to form a salt and to form water. So if we have a look at the method, okay, it says put the acid in a conical flask and warm it using a water bath. Okay, why would you do that? Why would you warm up the acid before adding the base? You would do that to speed up the reaction. So this relates to CC8, which is a paper 2 topic. But if you heat up the acid, it gets all of the particles moving, and that will increase the frequency of the collision. So if you've got a warm acid, you're adding the base to a warm acid, the reaction is going to be faster. I warm it up in a water bath because that's the safest method of warming an acid. It's safer than using a Bunsen burner. Then I add excess base to the acid and stir. So that word there, excess, just means more than you need. So you basically add quite a good bit of your base to the acid and you are stirring. How are you going to know when you've added more than you need? Well, the base will stop dissolving. So as you add the base to the acid, it reacts with the acid and it forms salt and it forms water. When there is no acid left for your base to react with, then the base just stays as a solid base. So it will look like it has just stopped dissolving, okay? Now in reality, the base doesn't dissolve in the water. The base is reacting with the acid. That's why it's disappearing. When there's no acid left to react with, it is going to stop disappearing. So it will stay solid. At this point then, so I've got my beaker, okay? I started off with just acid. Now I have got salt and water. All of that acid has been reacted, but because I've added more base than I need, I've got some solid base sitting at the bottom of my beaker, some unreacted base sitting at the bottom of my beaker. Now I want to get just pure salt, so I need to get rid of the water that I've made and I need to get rid of this solid base. So how am I going to do that? Well, the first thing I'm going to do is get rid of the solid base. So I'm going to filter my mixture. And when I do that, I'm going to get rid of the base. Oh, I think I have, yeah, I do have a little diagram here. I'm going to filter my mixture. The solid base is trapped here in my funnel. And then at the bottom, I just get the salt and the water. So in this case, they were making copper sulfate. Copper sulfate solution is the salt dissolved in the water. If I've just got salt and water, how am I going to get rid of the water? This is back to CC2 separation techniques. You heat to evaporate some of the water. So you have to specify heat. Don't just say evaporate without saying how you would do it. You heat to evaporate some of the water and then you let the rest of the water evaporate slowly to form large crystals. If you heat it too quickly, you end up just forming kind of a mush. So you want to heat it nice and slowly. So that there is your entire method. And you do need to know it. You can be asked a 6-mark question just asking you to describe how you prepare a salt. So these are the steps that you would follow. Other questions that they can ask you are as follows. So I'm going to get you to have a go at doing some of these questions yourself, and then I'm going to go through the answer. But these questions here at the start are quite typical. They'll tell you the salt that they want you to make, but they want you to suggest the acid and you to suggest the base. So they're telling you they want to make the salt copper sulfate. So what acid would you need to make that salt? Well, if it ends in sulfate, then the acid you would need would be sulfuric acid. So the first 3 questions are similar to that. Then in questions 4 and 5, you're asked to suggest a base. So you're trying to make the salt calcium sulfate. What base could you use? Your base has to have calcium in it, but then we saw that to be a base, it's a metal oxide, metal hydroxide, or metal carbonate. And it doesn't matter which of those words you choose. You could use calcium oxide, calcium hydroxide, or calcium carbonate. They were all bases and they will all give you calcium in your salt. Okay, so have a go at the rest of those questions yourself. Press play when you're ready to see the answers. Okay, so here are the answers. I've already done the first one. In question 2, you're asked to make a salt that's a nitrate, so you're going to use nitric acid. And in 3, you want to make a chloride salt, so you'll use hydrochloric acid. I did number 4 for you. In 5, it's the same idea. You want magnesium in your salt, so you need a magnesium base. That can be magnesium oxide, magnesium hydroxide, or magnesium carbonate. Safest way to warm up your acid before reacting it is just with a water bath. It's just safer than using an open flame. The reason you do it is to speed up that reaction. By excess, it means more base than you need. So you end up putting more base in there than you actually need. You've got some base left over at the end. The reason you add excess base is you want to make sure all of the acid has been neutralized, that all of the acid has reacted. How do you know when you've got extra base? It's going to stop disappearing. The answer for 11 is also the same. So you know it's in excess and you know the reaction is complete when that base stops disappearing. You filter then to remove the excess base. Okay, all of the acid is already reacted. The solid you are left with is the extra base and you filter to remove it. So say this again. You remove the unreacted base. The base is the one that's in excess. The acid has totally reacted. How are salt and water separated? The technique is called crystallization, and you leave the water to evaporate slowly so that large crystals were formed. Okay, if you were asked for 3 marks to describe that process, you would have to say heat, evaporate half of the water, allow the rest to evaporate slowly, and then leave your crystals to dry. So make sure you're explaining that process in detail if you are asked to. So we've looked at preparing a salt from an insoluble base. Now we're going to look at preparing a salt from a soluble base. And again, there's a special word for bases that dissolve in water, and they are called alkalis. And this method actually has a specific name. It's called a titration. So the actual reaction that you're going to be doing is exactly the same. You're going to react an acid and a base together, and you're going to form a salt and water. The difference here is that if you've got a soluble base, you are going to have a liquid. So in the last example, we had, our acid was always in liquid form, and we were adding a solid to the liquid. In this case, you've got your acid in liquid form, and now we're going to be adding another liquid into the acid. So you're adding a solid to the acid in the first method, and now you're going to be adding a liquid version of the base into the acid in the second method. And this is going to change things, okay? It's going to change things quite a lot, the fact that we've got a base that's in liquid form. It's dissolved in water. So what you're going to use, actually I'm going to show you a picture of it here, is you're going to use this apparatus. So it's quite different than what we had before. You've got what's called a buret, which is a long, thin piece of glassware that has a tap at the bottom, and then you've got your conical flask. And what you're going to do is you're going to put your alkali into the conical flask. So in here, I've got my alkali. And then in my buret, I have got my acid. And you're going to be adding the acid to the alkali really slowly. That's why this buret has a tap. You can open the tap and allow the acid into the alkali really, really slowly. As well as having the alkali in here, you're also going to have an indicator. And the indicator that we use is phenolphthalein. Phenolphthalein. And phenolphthalein in an alkali is pink. And when we add the acid to the alkali and the acid neutralizes the alkali, we get a color change from pink to colorless. And it tells us that our acid has reacted. Sorry, it tells us our alkali has reacted, and now that we've got an acid instead. So in the previous method, we didn't use an indicator at all, but now we are using an indicator. So we'll start with why. Okay, in the previous method, we knew the reaction was complete when the base stopped disappearing. We were adding a solid into a liquid. When that base stopped disappearing, we knew the reaction was complete. In this case, you're adding a liquid to a liquid, so there's nothing to see. Because there's nothing to see, you need to have an indicator, and the indicator we use is phenolphthalein. We don't use universal indicator because universal indicator is a range of different colours. Phenolphthalein is just pink in an alkali, colourless in an acid. You get one sharp colour change. It makes it easy to see when the end point has been reached. The other big difference is the fact that we're using this glassware. In the previous method, we just had a spoon and we were just adding base in. And we were adding base in excess, so more base than we needed. And it didn't matter that you were adding too much because at the end of the reaction, you just filtered to remove that extra base that you didn't need. In this case though, you're adding a liquid to a liquid. If I add too much acid, I've got no way of removing it again. I can't separate those two liquids. So therefore I need to add it in exactly the right amount. If I add too much, I can't go back. That's why we use this Buret with the tap, and you can add it nice and slowly. So if we look at the method, you're going to put your acid in a Buret, okay? And the Buret is used because it's got that tap, okay, which allows you to add nice and slowly. It's also got what we call graduations all up the side, which allows you to take an accurate reading of volumes. You can see exactly how much of that acid you are adding. You put a known volume of an alkali in a conical flask with a few drops of indicator. So I've got the acid in the Buret, I've got the alkali in my conical flask, and as I said, the indicator that we're going to be using is phenolphthalein, which will start off bright pink because it's an alkali. You then add the acid to the alkali until you see a colour change. It's going to go from pink to colourless. And then you note the volume of acid that you added. So just say it took 22 centimetres cubed of acid before you saw that colour change, you would write that down. And then you do the whole thing all over again until you have 3 almost identical volumes, okay? The reason you do them again is your first titration is typically not accurate. You end up adding it too quickly and you shoot past the end point. So the first time you do it, just say it was 22 centimetres cubed of acid that you have to add. The second time you do it, when you get to around 17 centimetres cubed, you're going to slow right down and start adding the acid really, really slowly. And you might find it that in your second go, that it took 21.5 centimetres cubed for that colour to change. This is already more accurate. Then you do it again and you see that it took 21.2 centimetres cubed. And then you do it again and you see that it was 21.3 centimetres cubed. Okay, so you do it 3 times until you've got 3 almost identical volumes. Once you've done it 3 times and you know exactly how much acid is required for this neutralization reaction, then you do the titration again, but this time you don't use the indicator. You don't need the indicator because you already know the volume required. So you don't need the indicator, you know what volume is going to be your endpoint volume. So you don't need it. And if you included it, then in your conical flask at the end, you've got salt, you've got water, and you've got indicator. Remember, the whole point of this is making a pure salt. If you end up with salt, water, and indicator, you're not going to be able to separate the salt from the indicator. So you do it again without the indicator, knowing the volume that's required, so that you don't have to remove the indicator. So you repeat the titration without the indicator, and then you're left with just salt and water. So you evaporate the water from the solution and you are left behind with just the salt. So I've got some questions here. Have a go at answering these 10 questions and then press play when you're ready to see the answers. Okay, so the glassware it's called a Buret. Why is it suitable? You get accurate volumes because you've got all of those graduations on the side and you can add it slowly through the tap. Indicator is phenolphthalein. And you need that indicator to show when all of the acid and the alkali have reacted to see when the end point is reached. It starts out at pink, it turns colourless, and it's preferred to universal indicator because you get a sharp end point. You just get one quick colour change.
You sometimes can put I didn't mention this, a white tile under the conical flask so that you can clearly see the colour change. You do it 3 times to get an accurate volume, so then you can do the titration without the indicator and you know exactly how much acid is required. If you want to get the pure salts, you need to remove the water, and that technique is called crystallization. Okay, I'll just show you the answers to part B as well. So I've asked you to describe a method, and you're told that you've got an alkali sodium hydroxide, so you know you've got it in liquid form. So I'm taking a liquid base and I've got my acid, which is a liquid, so I've got 2 liquids together, so I know I'm going to be using a titration. So I put my acid in my Buret. Sorry, this is all just what I have written before. Okay, that's what you would need to write out, describing how you would do that titration. Why is an indicator required in the reaction between an alkaline and acid, but not between an insoluble base? This is what I was talking about. You need the indicator in the titration to detect the end point. You don't need it when you've got an insoluble base, because you can detect endpoint when that solid base stops disappearing. So when you're adding the solid to the liquid, it's disappearing, and then it stops disappearing and remains solid. That tells you the reaction is done. When you're adding 2 liquids together, there's nothing for you to see unless you use an indicator. Why do you need to do it in the exact quantities? Say with the other method, we just threw in some with a spoon. It wasn't very precise at all. Now we're doing it incredibly precisely. And the reason is if you add too much, if you added too much acid or too much alkali, you can't separate them again. With the other method, because you're adding a solid to a liquid, you are able to use filtration at the end to separate. You can't do that in this case. Therefore, you have to measure the exact quantities. You have to make sure you do it accurately and you get it right. And yeah, that is it for the experiments. One more video left in the acids topic. It's about precipitation reactions. So precipitation and solubility will be the last video.